Tonight, we are going to measure the universe from a single star out to a wall we can never see past. 200 years ago, the best guess for the size of everything was about 6,000 light years across. It was wrong by a factor of more than 10 million. By the end, you will know how we found the real number and where the measuring stops. Go outside on a clear night and look up, and you will see something the whole of astronomy struggled with for 2,000 years. You can see the stars. You cannot see how far away they are. Depth is the one thing the sky refuses to show you. Every point of light sits on the same black surface, at the same apparent distance, and nothing about looking at it harder will tell you which ones are near. That is the problem this whole story begins with. Not what the stars are made of, and not how they burn, just how far. Everything else waits behind that one number, because until you know the distance to a single star, you cannot know the size of anything. There was an idea for how to do it, and it is older than the telescope. Hold your thumb up at arm's length and look at it with one eye closed. Then swap eyes. Your thumb jumps sideways against the wall behind it. It has not moved. You have. The jump happens because you looked from two slightly different places, and the closer the thumb is to your face, the bigger the jump. Now make the two places much further apart. The Earth sits on one side of its orbit in January and the other side in July, and those two positions are separated by about 300 million kilometers. If you look at a nearby star in January and then look again in July, it should shift very slightly against the stars behind it. Measure the shift, and simple geometry gives you the distance. No assumptions, no guessing about how bright the star really is. Just an angle and a triangle. The Greeks understood this. Aristarchus of Samos argued that the Earth moved around the sun, and his critics had a clean objection ready. If the Earth really swung from one side of the sun to the other, the stars would have to shift. Nobody could see any shift at all. So either the Earth was standing still, or the stars were unimaginably far away. They took the first answer. It is easy to be superior about that now, but look at what the second answer actually demanded. For the shift to be invisible to the naked eye, the stars had to be hundreds of thousands of times further away than the sun. There was no reason in the world to believe that. The universe would have to be almost entirely empty space, with a vast dark gap between the last planet and the nearest star, and nothing in the gap at all. That is exactly what it is. But there was no evidence for it, so the sky stayed small. Tycho Brahe is the one who really settled the matter, or thought he had. He spent decades making the most precise, naked eye measurements anyone has ever made. His accuracy ran to about an arc-minute, which is close to the physical limit of the human eye. He looked for the shift. He did not find it. And because his instruments were good, he trusted the result and concluded that the Earth does not move. His measurements were excellent. His conclusion was wrong. The shift was there the whole time, roughly 100 times smaller than anything he could detect. It is worth sitting with how small the thing being hunted actually is. The shift for even a nearby star is under 1 second of arc. A second of arc is 1/3600th of a degree. If you held up a coin at a distance of 4 kilometers, the coin would be about that wide. That is the measurement. Twice a year, for years on end, find one faint star among thousands. Record its position against its neighbors to within a coin at 4 kilometers. Then do it well enough to tell a real shift from your own telescope flexing in the cold. It took until 1838. Friedrich Bessel did it, And the way he chose his target is the good part. He could not measure every star, so he needed to guess which one was close before he started. He picked a faint, unremarkable star in the constellation Cygnus, called 61 Cygnus, and he picked it because it was moving. Stars drift very slowly across the sky over centuries, and a star that appears to drift quickly is probably not moving faster than the others. It is probably just nearer, in the same way that a low aircraft seems to cross the sky faster than a high one. 61 Cygni had one of the largest drifts anyone had catalogued. It was a bet, and it paid. Bessel measured a shift of about 1/3 of a second of arc. From that, he calculated a distance of roughly 10 light years. The modern value is a little over 11, so he was close, and he was the first person in history to know how far away a star was. Think about what he had just found out. Light from that star had been traveling for a decade before it reached his eye. He was not looking at 61 Cygni. He was looking at a photograph of it, taken 10 years earlier and delivered late. And 61 Cygni is a neighbor. It is one of the closest stars there is. That is worth slowing down for, because it changes what the night sky is. It is not a view, it is a stack of old messages, each one carrying a different date, all arriving at once. The star beside it in the same constellation might be 400 years further off, so its light left before the telescope was invented. You cannot see the sky as it is now. Nobody ever has, and nobody ever will. There is no way to correct for this. There is no vantage point that shows you the present. The delay is built into distance itself, and the further you look, the older the news gets. By the end of tonight, we will be reading messages that are 13 billion years late. That is not a flaw in the method. It turns out to be the single most useful thing about it. Within a couple of years, 2 other astronomers landed distances as well, one for Alpha Centauri and one for Vega, and the answer came back the same each time. The nearest stars are a few light years off. The empty gap the Greeks refused to believe in is real, and it is enormous. So now you have a yardstick. You also have a problem, which is that it barely reaches anything. Parallax works beautifully, and it works only nearby. Push out to a few hundred light years, and the shift shrinks below what any 19th century telescope could see. Beyond that, the method simply stops. You are standing in a dark field with a ruler that measures the first few paces and nothing after that. William Herschel had already run into this from the other direction, 50 years earlier, and his response was the first serious attempt at the size of everything. Herschel could not measure distances, so he counted instead. He pointed his telescope at a patch of sky, counted every star he could see in it, called the number out, and moved to the next patch. He did this for 683 separate fields. He called them star gauges, and the logic is simple and rather beautiful. If the stars are spread out evenly, then the direction with more stars in it is the direction where the system is deeper. Count in every direction, and the shape of the whole thing falls out of the numbers. Notice that he called the numbers out, rather than writing them down. He was at the eyepiece in the dark, often for whole nights in an English winter, and he could not stop to write. Somebody else had to be at the desk. That somebody was his sister. Caroline Herschel sat below the telescope with the record books, the clock, and the reference tables, taking down every figure her brother called into the night. She did the arithmetic. She reduced the raw numbers into positions, kept the catalogs in order, and worked out which of the night's objects were new. Without her, there is no data, only a man in the cold saying numbers to himself. She was not only a clerk. Working on her own, she found 8 comets and 14 nebulae. She produced a catalog adding more than 500 stars the standard list of the day had missed, and she became the first woman in Britain paid a salary for scientific work. She outlived her brother by decades and kept working. Hold on to her, because this happens again. The measurement that finally breaks the story open 80 years later comes from another woman at another desk, handed the tedious part of somebody else's project. That is not a coincidence, and it is not sentiment. The people given the counting are the people who end up looking hardest at the numbers, and the numbers are where the universe keeps its secrets. It worked. He found far more stars along one band of the sky than anywhere else, which is why the Milky Way looks like a band. From that, he concluded we sit inside a flattened system, shaped roughly like a grindstone. That is genuinely correct. The Milky Way is a disk, and Herschel found its shape by arithmetic from a garden with a homemade telescope before anyone knew what a galaxy was. Then he put a size on it, and the size was out by 7 orders of magnitude. His disk came out a few thousand light years across, with the sun close to the middle. The real disk is around 100,000 light years across. The sun is nowhere near the center, and the disk itself is one of a great many. Every part of that answer was wrong except the shape. The reason it was wrong is the most important thing so far, because the same reason comes back at every stage of the story. Herschel's method has an assumption buried inside it, and the assumption is invisible from within the method. He assumed he could see all the way to the edge. When the stars in a given direction ran out, he read that as the edge of the system, but the stars did not run out. They faded out. The disk is full of dust, thin and cold, and spread over enormous distances. Dust dims starlight with distance, and it does so in a way that looks exactly like stars thinning towards a boundary. Herschel was inside a fog, measuring the fog and calling it the far wall. Nothing in his data could have told him. The numbers were good, the counting was careful, the geometry was sound. The error was not sloppiness, it was structural, and it was undetectable from the inside. To his credit, he came to suspect it himself. Late in his life, he stopped claiming he could see the boundary and admitted that his telescope might be running out of reach before the stars ran out of space. He never resolved it. He could not have. Fixing it needed a way to measure distances far beyond parallax, and that did not exist yet. So here is where the story stands. There is one method that gives real distances, and it reaches only the nearest few hundred light years. There's one method that reaches further, and it gives an answer that is off by 7 orders of magnitude. Between them sits the entire universe, unmeasured. What was needed was something in the middle, a star that tells you how bright it truly is. Compare that against how faint it looks, and the difference gives you a distance. A star that carries its own label. Nobody was looking for one. It was found anyway by someone who was not allowed to use the telescope. The answer came out of a room with no telescope in it. At the Harvard College Observatory, at the turn of the last century, the director had a problem of volume. Photography had arrived, and photography does not get tired. A single night could produce plates holding thousands of stars. Every one of those stars needed its brightness and its position measured by hand. More plates were arriving than anyone could ever look at. The observatory was drowning in its own data. So they hired people to do nothing but measure. They were called computers, because that is what the word meant then. It was a job title, not a machine. The work was tedious, repetitive, and badly paid. And because it was all 3 of those things, the people hired to do it were women. The rate was something like 25 to 50 cents an hour. That was less than half what a man doing the same work would have been given. They sat at long tables in daylight. The plates lay in front of them, glass negatives of the night sky, and they worked through them one small square at a time with magnifiers and reference scales. They were not permitted to observe. The telescope was not theirs. They were handed the results of somebody else's night and asked to turn them into numbers. The room deserves a moment because it was not a room full of assistants. Annie Jump Cannon sat in it. She classified something like 350,000 stars by hand, and while she was doing it, she worked out the sequence that sorts them by temperature. Every astronomer alive still uses her scheme. Antonia Mori sat in it, and her refinement of that scheme was overruled by the director and turned out to be right. The women in that room were called Pickering's harem by people who found the arrangement amusing. So the room where the modern map of the sky was built was a room where nobody was allowed to look at the sky. One of them was Henrietta Swan Leavitt. She had studied at the college that became Radcliffe. She had lost most of her hearing after an illness in her 20s, and she began at the observatory as an unpaid volunteer before being taken on properly at the going rate. Her assignment was variable stars, which are simply stars that change brightness. More precisely, it was the variable stars inside two hazy patches of the southern sky called the Magellanic Clouds. The method was patient beyond description. Take a plate of the same patch of sky from two different nights. Lay one over the other. Anything that has changed brightness shows up as a difference in the size and darkness of its dot. Find those, measure them, log them, then do it again for years. She found more than 1,700 variable stars in the clouds. Nobody had asked her to find a law. She had been asked to make a list. Inside the list was one particular kind of star. Cepheid variables do not flicker at random. They pulse. The whole star swells and contracts on a cycle, and the cycle can run from a day or two out to several months. What matters is that it is extraordinarily regular. You could set a clock by one. Time it for long enough, and you know its period to within hours. It is worth knowing why they do it, because the reason is a kind of trap the star cannot get out of. Deep in its outer layers there is helium, and whether that helium holds on to its electrons depends on how hot it is. When the star contracts, it heats up, and the helium loses its grip on them. Stripped of electrons, the gas turns opaque. Light coming from below can no longer get through, so it pushes instead, and the whole outer envelope is driven outward. Then the star expands, and expanding cools it. The helium takes its electrons back. The gas turns transparent again. The light escapes without pushing, and the envelope falls back down under its own weight. Then it heats up, and it starts again. A valve made of light and helium, opening and shutting. It cannot settle, and so it keeps time. You have almost certainly seen one. Polaris, the North Star, is a Cepheid. It is pulsing while you look at it, though far too gently to notice, and it has been keeping that rhythm for the whole of recorded navigation. Here is what Leavitt noticed. The Cepheids with the longer periods were consistently the brighter ones. Slow pulse, bright star, fast pulse, faint star, not roughly and not on average, reliably across every one she checked, tightly enough to draw a line through the points. On its own, that is a curiosity about stars. What turned it into a yardstick was a second thought, and the second thought is the one that shows what she actually was. All of these stars sat inside the Magellanic Clouds. Those are worth a word too. From the southern hemisphere, they are visible to the naked eye on a dark night. Two soft detached patches of haze well away from the band of the Milky Way. Southern navigators had used them for centuries. They carry the name of Magellan's crew because that expedition brought a description of them back to Europe, though of course, they had been known to the people who lived under them for far longer than that. Nobody in 1912 knew what they were. They're galaxies, orbiting ours. Whatever the clouds turned out to be, Everything in one of them is at roughly the same distance from us. It is the same way that everyone in a distant town is roughly the same distance from you, even though some are at the near end of it. So the differences in how bright those stars looked could not be caused by some being nearer. They had to be differences in how bright the stars truly were. Which means the period is telling you the star's real output. Not how bright it appears from here, how bright it is. Now, put that to work. Find a Cepheid anywhere at all. Time its pulse, which needs nothing but patience and a clock. The period tells you how bright it really is. Compare that against how faint it looks from here. The gap between the two has only one cause, and the cause is distance. Light spreads out as it travels, and it dims with distance in a way we can calculate exactly. So the gap gives you the number. A star that carries its own label. That is what she found in a room she was not allowed to point a telescope from. The reach is the thing to hold on to. Parallax, the honest method we started with, gives out after a few hundred light years. Cepheids are enormous stars, thousands of times brighter than the sun. They can be picked out at millions of light years. So in a single step, the measurable universe went from the nearest neighborhood to something almost unrecognizably larger. She published the pattern quietly in 1908. The paper is mostly taken up with the list itself, and the sentence about brightness and period sits inside it almost as an aside. She quantified it properly 4 years later, in 1912, using 25 Cepheids in the smaller of the two clouds. That second paper is 2.5 pages long. Her name is not on it. The director's name is on it. Inside there is a note saying the work was prepared by Miss Leavitt. She never used what she had built. She was moved on to other projects. She spent years on the tedious business of standardizing brightness scales between observatories, which mattered and which nobody remembers. And she died of cancer in 1921 at 53 before anyone had turned her relation on the spiral nebulae. Edwin Hubble used it to do exactly that. He said afterwards that she had deserved the Nobel Prize. By then, she was not eligible. The prize is not awarded to the dead. There is a version of this where the injustice is the ending. It is worth resisting because it makes her smaller than she was. The interesting thing about Leavitt is not that she was overlooked, it is that she was right from a desk about the size of the universe, using materials somebody else had gathered for an unrelated purpose. Remember Caroline Herschel at the foot of her brother's telescope with her record books? This is the same shape a second time, 80 years on. And it's not a coincidence. Somebody has to be the one who actually looks at the numbers. The person handed the counting is the person who ends up staring at the data until the pattern becomes obvious. Patterns do not care who is permitted to use the instrument. There is one flaw in the new yardstick. It comes back in a serious way much later, so it is worth naming now while the tool is still shiny. Leavitt's relation tells you the difference in true brightness between two Cepheids. It does not tell you the absolute value for any single one. It is a scale with beautifully even markings and no zero on it. To fix the zero, you need one Cepheid whose distance you already know by some other route. And the only other route available was parallax, which barely reaches the nearest Cepheids at all, and had to be pushed to its absolute limit to reach even one. So the grandest measuring device ever built was anchored, right at its base, to a handful of the hardest and least certain measurements in astronomy. Everything stacked above it inherits whatever is wrong down there. Nobody worried much about that at the time. There was something far more exciting to argue about, and the argument was about a single faint smudge in the constellation of Andromeda. Point a decent telescope anywhere away from the band of the Milky Way, and you will find faint gray smudges. Not points, the way stars are points. Small oval patches of light with soft edges. By the early 1900s, thousands of them had been cataloged. Many showed a distinct spiral pattern, wound like water going down a drain. Nobody knew what they were. There were two answers available. The gap between them is one of the widest gaps in the history of the subject. The first answer said, they are near. Clouds of gas inside our own galaxy, caught in the act of collapsing into new solar systems, spiraling as they fall. Under that reading, the Milky Way is everything there is. The smudges are local weather inside it. And the universe has one galaxy in it. The second answer said they are separate. Whole systems of stars as large as our own, so far away that the individual stars blur together into haze. Under that reading, the Milky Way is one of an enormous number. The universe is larger than anyone had let themselves write down. The same object, either way. Either a cloud a few thousand light years off, or a galaxy a million light years off. There is no middle position available, and for 2 decades, there was no way to choose between them. On the 26th of April, 1920, the two readings were argued out in public. It happened at the Smithsonian in Washington, in front of an audience of astronomers. It has been called the Great Debate ever since. Harlow Shapley took one side. Heber Curtis took the other. Shapley argued that the Milky Way is vast and that it is all there is. He had a real reason for the first half of that, and it is some of the best work in this whole story. He had turned Leavitt's Cepheids on globular clusters. Those are tight spherical swarms of very old stars scattered around the sky. He measured their distances, then he plotted where they sat. And they are not spread evenly around us. They pile up heavily towards one direction in Sagittarius. The obvious reading is that the swarms are arranged around the center of the galaxy, which means the center is over there, tens of thousands of light years away, which means we are nowhere near it. That is correct, and it is a demotion on the scale of the one Copernicus delivered. The Earth had already been moved out of the middle of the solar system. Shapley now moved the Sun out of the middle of the galaxy. We are in the suburbs, a long way out along a spiral arm. The bright, crowded center of our own galaxy is a place we have never been anywhere near. Sit with that for a moment. Everything anyone had ever seen, every star anyone had ever named, was a local sample taken from an unremarkable spot well off to one side. Having made the galaxy that big, Shapley then made it bigger. He put it at around 300,000 light years across, which is about 3 times the real figure. And once your galaxy is that enormous, the spirals cannot be separate things. To sit outside a system that large, they would have to be at distances that looked absurd, so he read them as gas clouds close to home. He had one other piece of evidence, and it was simply wrong. A colleague named von Manen had reported measuring the rotation of spiral nebulae on photographic plates. He claimed to have watched them visibly turn over the course of a few years. If a spiral really turns fast enough to see, it has to be small and near. A galaxy-sized object turning at that rate would have its outer edge moving faster than light, which is not permitted. So the measurement was strong support for the nearby reading, and Shapley trusted it. It was an artifact. It took years to be abandoned, and while it lasted, it held the wrong answer firmly in place. Curtis argued the other side. His case rested on 2 things, and both of them turned out to be sound. The first was novae. A nova is a star that flares suddenly and dramatically, then fades. Nova had been recorded in our own galaxy, and novae had been recorded inside the Andromeda smudge. The ones in Andromeda were far fainter. Not a little fainter, thousands of times. So if novae are broadly similar wherever they happen, then whatever Andromeda is, it lies a very long way beyond the stars around us. The second was dust. Some of the smudges are turned edge onto us. Look at one of those and you see a thin, bright disk with a dark line running down the middle of it, a lane of obscuring material lying in the plane of the system. The Milky Way has exactly that. Go out on a genuinely dark night, look along the band, and you can see the dark rift with your own eyes. Curtis pointed out the obvious consequence. The spirals look like the thing we are standing inside, viewed from outside. It is a simple argument, and it is a very hard one to answer. He also argued the galaxy was much smaller than Shapley claimed, about 30,000 light-years. He was wrong about that. So the debate ended with each man holding one true half and one false half. Shapley was right that the galaxy is large, and that we sit well off its center, and wrong that it is everything there is. Curtis was right that the spirals are separate galaxies, and wrong about the size of our own. Neither of them could finish the argument. Both were reasoning from indirect evidence, and the evidence pointed in two directions at once. That is the honest state of the science in 1920. Two careful people looking at the same sky, disagreeing about whether the universe holds one galaxy or millions. No way to settle it. And notice that this is the same failure as Herschel's, wearing different clothes. Every argument in the room depended on an assumption that could not be checked from inside the argument. What was missing was not cleverness. Both of them were clever, and both had thought about nothing else for years. What was missing was a single measurement of a single star. If you could pick out one individual Cepheid inside one of those smudges and time its pulse, then Leavitt's relation would hand you the distance. The argument would be over in an afternoon. There would be nothing left to say. The number would land either inside Shapley's galaxy or outside it, and that would be that. The difficulty was resolution. To find one star in a spiral nebula, you have to separate it from the haze of all the others. And the haze is precisely what makes a smudge a smudge. That needs a larger mirror than anyone had yet used. It needs long exposures, and it needs an observer stubborn enough to come back to the same faint object month after month to catch a pulse in the act. All three of those arrived in the same place at the same time. On a mountain in California, in the hands of a man who had spent a decade being told he was insufferable. Mount Wilson stands above Pasadena in Southern California, and in 1917 it took delivery of the largest telescope in the world. The Hooker reflector has a mirror 100 inches across. Getting the glass up the mountain took a mule train on a dirt track. For nearly 3 decades, nothing on Earth could see further. Edwin Hubble arrived 2 years later to use it, and he was not universally loved. He had come back from the war, insisting on being addressed by his military rank. He wore tweeds and smoked a pipe and spoke in an English accent he had acquired in Oxford and never given back. Colleagues found him grand. Shapley, who had worked there before him, could not stand him. None of that matters to the sky. What matters is that he was patient and that he went back to the same object over and over. His target was the Andromeda Nebula, the largest and brightest of the spiral smudges. Through the 100-inch, it was no longer a featureless haze. Around its outer regions, he could begin to resolve individual points of light. That alone was suggestive, but points of light are not a measurement. He needed one of those points to be a Cepheid, so he photographed the same region again and again over months, and compared the plates looking for a dot that changed. In October 1923, he found one. He first logged it as a nova, a star that had flared. Then he kept watching, and it did not behave like a nova. It faded, and then it came back, and it came back on a schedule. The plate survives. He had written the letter N on it for nova. Then he understood what he was actually looking at, so he crossed the N out and wrote var for variable and put an exclamation mark after it. That exclamation mark is the moment the universe stopped being one galaxy. He timed the pulse, something around 31 days. Leavitt's relation turns that into a true brightness. Compare the true brightness against how faint the star looked from the mountain, and out comes a distance. His answer was about 900,000 light years. The real figure is closer to 2.5 million. We will come back to why he was out by a factor of nearly 3. The reason is the flaw in the yardstick, the missing 0 point, and it becomes a crisis later on. But for the argument in front of him, the error did not matter in the slightest. Shapley's galaxy was 300,000 light years across. Hubble's Andromeda was 900,000 light years away. Even at his too small number, even if you allowed Shapley's too large galaxy, the smudge was comfortably outside it. Andromeda is not a cloud inside our system. It is another system, and it is enormous, and it is one of thousands already cataloged. He wrote to Shapley with the result. Shapley read the letter and said it was the letter that destroyed his universe. That is a generous thing for a man to say about being proved wrong, and he had a lot to lose. He had built his reputation on the one galaxy picture, but he had also personally done the work that moved the sun off the center. He knew what a demotion looked like from the inside, and he recognized this one. Consider what had just happened to the scale of things in one step from one star. Before the plate, the Milky Way was the universe, 100,000 light years across, containing everything, and we were unfashionably placed within it. After the plate, the Milky Way is one object among a great many. Most of them are so far off that their light takes millions of years to arrive, and the space between them is mostly empty. The demotions now stack up. Copernicus moved the Earth out of the center of the solar system. Shapley moved the sun out of the center of the galaxy. Hubble moved the galaxy out of the being the universe. Each one was resisted at the time. Each one turned out to be a step towards a correct and much emptier answer. And notice how each step happened, not through argument and not through a better theory. Somebody measured a distance. There is a small, sad footnote. Leavitt had died 2 years before that plate was exposed. The relation that turned a smudge into a galaxy was hers, and she was not there to see it used. Hubble never met her. There is also a detail about the plate itself that is worth holding on to. Hubble did not discover Andromeda. Anyone can see it. On a clear autumn night, from a dark enough place, it is visible to the naked eye as a faint elongated blur in the constellation that carries its name. Human beings have been looking directly at another galaxy for as long as there have been human beings. The light reaching your eye from it tonight left about 2.5 million years ago. When it started out, there was nothing on Earth that would have recognized itself as a person. So we had always been able to see it. We simply had no way of knowing what we were looking at, and no way of knowing how far away it was. That is the whole of the difficulty in one object. Depth is invisible exactly as it was at the start of tonight, and everything depends on it. 2 things about Andromeda are worth knowing before we leave it, and both of them are quietly alarming. The first is its size. It is not a smaller companion to our galaxy. It is comparable, and by some measures larger, spanning perhaps 200,000 light-years against our 100,000. When Hubble resolved that one Cepheid, he was not finding a minor object at the edge of things. He had found the other large galaxy in our immediate neighborhood. The second is what it is doing. Almost every galaxy in the sky is receding, as we are about to see at length. Andromeda is not. Andromeda is coming towards us at something like 110 kilometers a second. It's one of the few galaxies whose light is shifted towards the blue rather than the red. And the reason is simply that it is close enough to be gravitationally bound to us. The two galaxies are held together, orbiting a common center, falling slowly inward. The general stretching of space cannot pull apart things that gravity has already caught, so they will meet. In roughly 4.5 billion years, the two disks will begin to pass through one another. That sounds like a catastrophe, and on the scale of stars, it is almost nothing. The space between stars is so vast that individual collisions will be extraordinarily rare. Nothing will crash. The two galaxies will slide through each other, pull each other out of shape, swing apart, and come back. And over a further few billion years, they will settle into one larger galaxy with no spiral arms left. Anyone watching from a planet here would see the sky slowly fill. Andromeda would grow from a faint smudge into a second Milky Way spread across the whole sky, brightening over 100 million years, until there was nowhere to look that was not full of stars. It is the largest event in the future of this galaxy, and it is already scheduled, and it is already visible as the smudge you can see with your own eyes tonight. With Andromeda measured, the technique could be pointed at the other spirals, and Hubble spent the following years doing precisely that. Distance after distance. A catalog of galaxies with real numbers attached, spreading outward from us in every direction. And when he laid those distances beside a set of measurements, somebody else had been quietly collecting for a decade. An entirely different and much stranger fact fell out of them. While the debate about the smudges was going on, a quiet man in Arizona had been collecting a set of numbers nobody could interpret. Vesto Slifer worked at the Lowell Observatory in Flagstaff, and from about 1912, he had been taking spectra of the spiral nebulae. A spectrum is what you get when you spread light out into its colors. It is a far harder measurement than a photograph, because you are taking light that is already faint and splitting it into a band, which makes every part of it fainter still. Some of his exposures ran for 20 or 30 hours, spread across several nights. What he was looking for was the pattern of dark lines that cuts across every stellar spectrum. Those lines are the fingerprints of elements. Hydrogen absorbs light at particular colors, and nothing else does. So hydrogen leaves gaps in exactly the same places every time. Calcium leaves a different set. The positions are fixed by physics, and they do not vary. You can measure them in a laboratory on a bench and get the same answer, which makes them a reference. Suppose you find the hydrogen lines in a star's spectrum sitting slightly away from where the laboratory says they belong. Something has moved them, and the only thing that moves them is motion along your line of sight. If the object is coming towards you, the whole pattern shifts towards the blue end. If it is going away, the pattern shifts towards the red. It is the same effect you hear when a siren passes and drops in pitch, only done with light instead of sound. The size of the shift tells you the speed. Slifer measured spiral after spiral. Almost every one of them was shifted to the red. They were going away, and they were going away fast, some of them at 1,000 kilometers a second, which was far quicker than anything anyone had measured in the sky before. He published the results, and nobody knew what to do with them. It is worth being clear that he had the central observational fact of modern cosmology in his notebooks years before it meant anything. What he did not have was distances. A list of speeds with no distances attached is a curiosity. It tells you the spirals are moving and nothing else. Hubble had the distances. He was working with Milton Humason by then. Humason had started at Mount Wilson as a mule driver, carrying equipment up the mountain, and had taught himself to become one of the finest observers there. Between them, they put the two lists side by side. Slipher's speeds, Hubble's own Cepheid distances, and they plotted one against the other. The points fell on a line. The further away a galaxy is, the faster it is receding. Double the distance and you double the speed. That is the relation he published in 1929, and it is about as simple a result as it is possible to get from the sky. It is also, on first reading, a very strange thing to be told, because it sounds as though we are being avoided. If everything is running away from us specifically, then we appear to be at the center of something. That was the immediate worry, and it took a while to talk people out of it. The resolution is the most important idea in the whole story, so it is worth going slowly. Take a rubber sheet and mark it with dots. Now stretch the sheet evenly in every direction. Pick any dot you like and stand on it. Every other dot moves away from you. And the dots further off move away faster because there is more rubber between you and them, and all of that rubber is stretching at once. Now move to a different dot and look again. You see exactly the same thing. Everything receding, the far ones fastest, yourself apparently in the middle. There is no center on that sheet. Nothing is moving through the rubber. The rubber itself is getting larger, and every point is being carried along with it. The appearance of being at the center is not a clue about your position. It is what stretching looks like from anywhere inside it. That is what the redshifts are telling us. The galaxies are not flying outward through space, away from a place we happen to occupy. Space between them is expanding, and they are being carried apart by it. Everyone everywhere sees the same recession, and nobody is in the middle because there is no middle to be in. Hubble himself was careful about saying any of this out loud. He wrote about the numbers and stayed cautious about what caused them, and he stayed cautious for years. The interpretation was worked out by other people, and one of them had already got there from pure theory before the observations were published at all. Georges Lemaitre was a Belgian priest and physicist, and he had fought in the First World War before taking up cosmology. In 1927, he worked through Einstein's equations and found that they permitted a universe which expands, not as a curiosity, as the natural solution. He also went further, took the handful of galaxy velocities and distances that existed at the time, and derived a rate of expansion from them. That is 2 years before Hubble's paper, with the same relation and a broadly similar number. Almost nobody read it. He had published in French, in a small Belgian journal, and the work sat there. When an English translation appeared 3 years later, the paragraphs containing his estimate of the expansion rate were missing from it. For a long time, that omission was assumed to be somebody protecting Hubble's priority. It appears Lemaitre cut them himself, on the grounds that by then, Hubble had measured the thing properly, and his own rough figure was no longer worth reprinting. Einstein's own reaction is the part most worth remembering. He had found the expanding solutions himself years earlier, disliked them, and inserted a term into his equations specifically to hold the universe still. When he was shown the evidence, he abandoned the correction. He is supposed to have described it afterwards as the biggest blunder of his life, though the phrase comes to us secondhand. The relation is now often called the Hubble-Lemaitre law, The name was formally changed by a vote of the International Astronomical Union in 2018, 91 years after the paper nobody read. Now follow the expansion backwards, because this is the part that changes everything. If the distances between galaxies are growing, then yesterday they were smaller. Last year they were smaller again. Keep running the film in reverse, and everything you can see gets closer together and denser and hotter. Push it far enough and there's no space between anything at all, which means the universe has a history. It has a state it was in, and it has not always looked like this. And more than that, it has a date. If you know how fast things are separating now, you can work out roughly how long they have been separating for, and that number is an age. The universe stopped being a permanent stage on which things happen. It became a thing that happened. There is one more consequence, and it's practical rather than philosophical. The relation cuts both ways. If speed depends on distance in a fixed way, then you can measure a galaxy's redshift, which is comparatively easy even at colossal distances, and read its distance straight off. That is the fourth rung. Parallax reaches hundreds of light years. Cepheids reach millions. Supernovae, which are still to come, reach further again. And redshift, once it has been calibrated by everything below it, reaches billions. It is a magnificent ladder. It also has a fault running through it, from the bottom to the top, and the fault is about to become impossible to ignore. The dark lines in a spectrum did something else as well, and it is stranger than measuring distance. They tell you what a star is made of, without going there, without a sample, from a smear of light spread out on a photographic plate taken through a telescope, from an object so far away that the light is older than the instrument that caught it. That should not be possible. And for a long time, nobody knew that it was. Joseph von Fraunhofer found the lines first in 1814, working with the finest glass in Europe. He was a lens maker rather than an astronomer, and he was trying to characterize his own materials. When he spread sunlight into a band, he found it was not smooth. It was interrupted by hundreds of narrow, dark gaps at fixed positions in the same places every time. He cataloged them and labeled the strongest with letters. Some of those letters are still in use. What he could not do was say what they were. The answer came from a laboratory rather than an observatory, more than 40 years later. Gustav Kirchhoff and Robert Bunsen were heating elements until they glowed and looking at the light. Each element gave its own arrangement of bright lines, always the same, never shared with another element. Sodium in one place, iron in a dense thicket of places, a fingerprint in light. Then they made the connection that matters. Pass white light through a cooler gas, and the same element removes exactly the colors it would have emitted. Bright lines become dark lines. The gaps in Fraunhofer's spectrum are elements in the sun's outer layers, absorbing on the way out. Which means the letters in the catalog are a list of ingredients. Take that in for a moment, because it is one of the strangest results in the whole of science, and it arrives without any fuss. There is no way to visit a star. There will never be a way to visit a star, and it does not matter, because every star has been broadcasting its own chemical composition in all directions, continuously, for its entire life, and all anyone had to do was learn to read. So by the early 1900s, the composition of the sun was considered known. The lines of iron and calcium and sodium and magnesium are strong. The line of hydrogen is present but unremarkable. The obvious reading is that the sun is made of much the same material as the Earth, with a similar mix of heavy elements, only very much hotter. That was the settled view. It was held by everyone who mattered. And it was wrong in a way that changes what the universe is. Cecilia Payne came to Harvard from Cambridge in 1923. She had gone to Cambridge to read science and had sat in on a lecture by Eddington about the eclipse expedition that confirmed general relativity, and she said afterwards that her world had been so shaken she barely slept for 3 nights. Cambridge would not give her a degree because it did not give degrees to women then, so she left for America, where there was at least a graduate program that would take her. She arrived into the same observatory and the same enormous collection of plates that Leavitt had worked through 20 years earlier. The problem she took on was the strength of the lines. Everyone had been reading line strength as a straightforward measure of how much of an element was present. More iron, stronger iron lines. It is an intuitive assumption, and it is the kind that hides. Because line strength does not only depend on how much of the element is there, it also depends on temperature and on how many of the atoms have been stripped of an electron. An atom that has lost an electron absorbs at different colors than one that has not. So at one temperature, an element may print a heavy signature, and at another temperature, the same amount of the same element may barely register at all. Payne worked through the physics of that, applied it across the whole sequence of stellar types, and corrected for it properly for the first time. The heavy elements were not abundant. Their lines were strong because the conditions happened to favor them. Hydrogen and helium were present in quantities nobody had allowed for. Not a little more. Something like 1,000,000 times more hydrogen than the heavy metals whose lines dominate the spectrum. Stars are not hot Earths. They are almost entirely hydrogen and helium, with a trace of everything else. She put it in her thesis in 1925. The leading authority on stellar composition in the world at the time was Henry Norris Russell, and he read the result and told her it was clearly impossible. So she wrote a hedge into her own thesis, saying the hydrogen figure was almost certainly not real. She was 25 years old. She was a woman in a field that had just refused her a degree, and the most powerful man in her subject had told her she was wrong. 4 years later, Russell arrived at the same conclusion by a different route and published it, and the result is very often attributed to him. He did credit her. He cited her work. But the way science remembers a result is not always the way the citations run, and for decades, the discovery that the universe is mostly hydrogen was Russell's. Otto Struve later called her thesis the most brilliant doctoral dissertation ever written in astronomy. She became the first woman to chair a department at Harvard, and she got there in 1956, 31 years after the thesis. That is the third time tonight. Caroline Herschel at the desk under the telescope, Henrietta Leavitt with the plates and the variable stars, Cecilia Payne with the line strengths. There is a fourth still to come, and she found that most of the universe is invisible. Measurements that each change the size or the contents of everything, all of them made from the unglamorous end of the work. There is a reason that keeps happening, and it is not a coincidence about individuals. The prestigious job was pointing the telescope. The unprestigious job was working through what came back. And the universe does not keep its secrets in the eyepiece. It keeps them in the data. One last thing, because it matters for everything after this. If the universe is overwhelmingly hydrogen, then the heavy elements are the exception rather than the rule, and they had to come from somewhere. Hydrogen is the simplest thing there is. Everything else is hydrogen that has been through something, which means everything heavier than helium had to be built somewhere, out of hydrogen, after the fact. Where that happened is a story for later tonight, and it is only possible because of a very long stretch, early on, in which nothing had happened at all. There is a consequence of everything so far that has been sitting quietly in the background since we began, and it is time to take it seriously. Light is fast, but it is not instant. It crosses the room you're sitting in about 1 billion times quicker than you could walk it, which is why the world looks like it is happening now, over the distances in this story that stops being true. Sunlight takes 8 minutes and 20 seconds to reach you. So the sun you see at midday is the sun as it was while you were doing something else. If it went out, you would carry on in full daylight for over 8 minutes, entirely unaware. Move outward, and the delay grows. The nearest star system is 4 years away. Andromeda is 2.5 million years away. The furthest galaxies in the deepest images are more than 13 billion years away. And in every case, what arrives is not the object. It is a report about the object, sent when the light left, and delivered at the end of a journey that took as long as it took. Earlier tonight, that was a stack of old messages arriving late. It is worth being harder about it than that. Every single thing overhead carries a different date, and the dates are not decorative. 2 stars side by side in the same constellation can be separated by thousands of years of postage. The pattern you are looking at was never simultaneous. It has never existed at any moment as the arrangement you can see. That has an unsettling side, and it is worth saying plainly. You will never see any of it as it is. There is no correction to apply. There is no place you could stand that would show you the present state of Andromeda, because getting the information here takes 2.5 million years, no matter who is carrying it or how clever they are. The delay is not a limitation of our instruments. It is a property of distance. Some of the galaxies in the deepest images have almost certainly changed beyond recognition. Some have collided with others and merged into something new. Some have run out of gas and stopped making stars. We are looking at portraits of objects that may not exist in that form anymore, and we cannot check. Now the other side of it, which is the reason astronomers are delighted rather than depressed by all this. If looking further away means looking further back, then distance is a time machine, not a controllable one. You cannot aim it at a date, but you can aim it at a distance, and the date comes with it. Look at galaxies nearby, and you see the universe as it is now. Look at galaxies a few billion light years off, and you see it as it was a few billion years ago. Look as far as the instruments reach, and you see it in something close to its infancy. Which means the history of the universe is not something to be reconstructed by argument. It can be observed directly. You take a survey at one distance, then a survey at another, and you compare. And the surveys do not match, which is the point. Galaxies at great distance look different from galaxies nearby. They are smaller, they are bluer, which means their stars are younger and hotter. They are messier, less often arranged into the tidy spirals and smooth ellipticals that dominate the local sky. Many are visibly in the middle of colliding. That is galaxy evolution, seen rather than inferred. The universe used to be a rougher and more chaotic place, and it settled down. The clearest single demonstration of all this came from pointing the best telescope available at nothing at all. In 1995, the director of the Hubble Space Telescope did something that a lot of people thought was a waste of an extremely expensive instrument. He chose a patch of sky in Ursa Major that was, as far as anyone could tell, empty. No known galaxies, no bright stars in the way. A dark, uninteresting scrap of nothing. The patch was about the size of a grain of sand held at arm's length, roughly 1/24 millionth of the whole sky. He pointed the telescope at it, and left the shutter open, on and off, for 10 days. The image came back with about 3,000 galaxies in it. Not stars, galaxies. 3,000 separate systems, each one holding many billions of stars, packed into a piece of sky you could hide behind a grain of sand. Spirals, ellipticals, irregular smears, some of them so faint and so red that their light had been traveling for the better part of the age of the universe. Later versions of the experiment went deeper and found more. The exercise has been repeated with better instruments, and the answer keeps being the same. There is no empty direction. Point anywhere, look long enough, and the frame fills with galaxies. The most recent round of this is worth a moment, because it is a live argument rather than a settled result. The James Webb Space Telescope sees in the infrared, which matters for a specific reason. Light from the earliest galaxies has been stretched by the expansion so far that it has left the visible band altogether. To the eye, and to any telescope built for visible light, the very first galaxies are simply not there. They emit nothing you could see. Webb was built to catch them where their light has actually ended up. It found them. Then it found a problem. Some of the earliest galaxies in those images look too big and too well organized for how early they are. Galaxies are supposed to assemble slowly, from small clumps merging over long periods. Several of the ones Webb has picked out appear to have got large within a few 100 million years of the beginning, which is very fast. Nobody is claiming this breaks anything yet. There are several ordinary explanations available. The brightness might be exaggerated by an unusually active center rather than by sheer numbers of stars. The distances rest on redshift estimates that can be refined. Early star formation might simply have been more efficient than the models assume, but it is the same shape as everything else in this story. A new instrument looks in a new way, and the numbers come back slightly wrong, and the disagreement is where the next correction will come from. Take that number and run it outward across the whole sky, and you get an estimate for how many galaxies are in the observable universe. It comes to somewhere in the hundreds of billions, and some surveys push it into the trillions. Every one of them is a Milky Way. Every one of them is full of stars, and the stars are full of planets, and all of it was invisible to everyone who ever lived before about a century ago. Herschel counted 683 fields by hand and concluded the universe was a few thousand light-years wide. One deep image of an empty patch contains 3,000 galaxies. That is the distance the argument traveled in 200 years, and it was traveled almost entirely by people measuring things more carefully than the people before them. There's one more thing hiding in the deep images, and nobody was looking for it. When you have a large number of galaxies with measured distances, you can start asking what holds each one together. A galaxy is a spinning object. Spinning objects fly apart unless something is holding on, so you can weigh a galaxy by watching how fast it turns. Somebody did that carefully for dozens of galaxies, and the mass came back wrong. Vera Rubin wanted to study galaxies, and the profession spent a long time making that difficult. She had been told, when she said she was interested in astronomy, that she should consider painting subjects from nature instead. The college she wanted for graduate work did not take women. Then she asked to observe at Palomar, which had the largest telescope in the world at the time. The answer was that there were no facilities for women there. What that meant was that there was no separate lavatory. She is said to have cut a paper skirt, stuck it to the figure on the door, and gone in. So she chose a problem nobody was competing for. That is the second thing worth noticing about her. The first is that she was very good. The second is that she deliberately went where the crowd was not, because the crowd was in her way. The unfashionable problem was rotation. How fast does a galaxy turn? And does the speed vary as you move out from the middle? We already know what the answer should be, because the same question was settled for the solar system 300 years earlier. Mercury goes round the Sun in 88 days. Neptune takes 165 years. The further out you go, the slower things move. And the reason is simply that gravity weakens with distance. Nearly all the mass is in the middle, in the Sun, so the outer planets feel a gentler pull and can hold their orbits at a gentle speed. Any system with its mass concentrated in the center behaves that way. Galaxies are obviously mass concentrated in the center. You can see it. The middle of a spiral is a bright, dense bulge, and the outskirts are thin and faint and mostly dark. So the stars in the outskirts should be moving slowly. Working with Kent Ford and using a spectrograph sensitive enough to catch the faint outer regions, Rubin measured it. She took spectra at points along a galaxy's disk and used the redshift trick from earlier, only now applied to two edges of a single object. One side of a spinning galaxy is coming towards you, and its light shifts blue. The other side is going away and shifts red. The size of the difference tells you the speed of rotation at that radius. She started with Andromeda, then worked through dozens more. The stars in the outskirts were not moving slowly. They were moving just as fast as the stars near the middle. The curve did not fall away. It went flat, and it stayed flat, right out to the visible edge and beyond, into regions where there is barely any starlight at all. That should not be possible. A galaxy rotating like that is rotating too quickly for the amount of matter you can see in it. The visible mass cannot supply enough gravity to hold the outer stars on their paths. They should have been flung off long ago. Every spiral we look at should have unwound itself into the void billions of years ago, and none of them have. There are only two ways out. Either gravity does not behave the way we think it does at these scales, or there is a great deal of matter in those galaxies that we cannot see. The second answer won, and the evidence for it kept arriving from directions that had nothing to do with rotation. Clusters of galaxies move too fast for their visible mass to hold them together, which Fritz Zwicky had already noticed in the 1930s and been largely ignored for. Light from distant objects bends around foreground clusters by more than their visible mass should bend it. The pattern of ripples in the oldest light, which we come to later tonight, only fits if most of the matter is of this invisible kind. 4 completely separate measurements, all of them saying the same thing. There is roughly 5 times more matter than there is matter we can see. The bending of light deserves a little more room because it is the most direct of the 4 and it does not depend on anything orbiting. Mass distorts the path light takes. A sufficiently heavy object sitting between you and something further away will act as a lens, bending the light around itself, so the distant thing appears smeared into arcs or duplicated into several images. This is not a subtle prediction that had to be dug for. It is visible in photographs. Point a good telescope at a rich cluster of galaxies, and you will see the background universe behind it, stretched into rings and streaks. The amount of bending tells you the amount of mass, and you can work it out without knowing anything about what the mass is doing. So it is a completely independent way to weigh a cluster, and the clusters come back far heavier than the galaxies inside them can account for. There is one particular object that settled the argument for a lot of people. 2 clusters of galaxies collided, and the collision separated the ordinary matter from the rest. The hot gas, which is most of the visible mass, got slowed down by the impact and left behind in the middle, glowing in X-rays. but the lensing shows the bulk of the mass carried straight on through, out ahead of the gas, sitting where the galaxies are. Which is what you would expect if most of the mass is something that does not collide with anything. The gas crashed, the dark matter passed through itself, and kept going. You can see the two components pulled apart in the same image, and it is difficult to explain that by adjusting gravity. It is called dark matter, which is an unhelpful name, because it sounds like a theory. It is not a theory. It is a measurement. It is the gap between how much mass a galaxy has and how much of that mass is glowing. And the gap has been measured many times over, mostly by people trying to make it go away. What is genuinely unknown is what it is made of. It does not emit light. It does not absorb light. As far as anyone can tell, it ignores ordinary matter entirely, except through gravity, which is why it can be sitting in the room with you doing nothing whatsoever. The best guess is a particle we have not yet detected. Enormous experiments have been built to catch one. So far, nothing has. So the honest position is this. Every star Herschel counted, every galaxy Hubble measured, every point of light in the deep field, all of it together is a minority component of the universe. The luminous part is the froth. Most of the mass is something else, and we do not know what. Rubin's own view of it was characteristically flat. She pointed out that in a spiral galaxy, about 95% of the mass is dark. Then she said that we had spent the whole of astronomy studying the 5% that shines, and now the pattern from earlier tonight, arriving for the fourth time. Caroline Herschel took down the numbers her brother called out of the dark and found 8 comets while she was at it. Henrietta Leavitt was handed the tedious business of listing variable stars and found the yardstick that measures the universe. Cecilia Payne was given the line strengths and found out what everything is made of. Vera Rubin took the unfashionable problem nobody wanted and found that most of the universe is invisible. None of the 4 was where the prestige was. All 4 were in the data. Rubin never received a Nobel Prize, and she died in 2016. Every year for a long stretch her name came up, and every year it did not happen. It is difficult to name a 20th century observation that changed the inventory of the universe more completely. What she found does not break the ladder, and that matters for where we are going. The distances all still stand, but the thing being measured is stranger than the measuring implied, and it sets up the problem that comes next. The ladder itself is more fragile than it looks. Cepheids are magnificent, and they run out. They are bright enough to be picked out across millions of light years. That was enough to settle the argument about Andromeda, and enough to map the nearby galaxies. But a Cepheid is still a single star. Push out past roughly 100 million light years, and even the best telescope can no longer separate one star from the glow of the galaxy it sits in. The dots merge. The yardstick becomes unreadable. And 100 million light years, which sounds enormous, is a small fraction of what there is. So the same problem as before returns, one story up. You need something visible at far greater distances, and you need to know how bright it truly is. The answer is a particular kind of exploding star, and the reason it works is almost suspiciously neat. Start with a white dwarf. That is what remains when a star like the Sun runs out of fuel and collapses. What is left is a dense cinder about the size of the Earth, holding roughly the mass of the Sun. On its own, it will simply sit there and cool for a very long time. Now, put it in a pair, orbiting another star, which is a common arrangement. The dwarf can pull material off its companion and add it to itself. It gets heavier. And here is the neat part. There is a hard limit to how heavy a white dwarf can be. Past it, the star's own gravity overwhelms the thing holding it up. That limit is the same everywhere in the universe, because it is set by physics rather than by circumstance. So, the dwarf accumulates mass, reaches the limit, and detonates. Every one of them detonates at very close to the same mass, which means every one of them releases very close to the same amount of energy. That is a standard candle, not a star that tells you its brightness by its rhythm, like a Cepheid, but a star that tells you its brightness by the manner of its death. They are called Type 1, a supernovae, and at peak, they can outshine the entire galaxy around them. A single exploding star, visible clean across the observable universe. You do not need to resolve it out of the haze. It is brighter than the haze. So the ladder is now 4 rungs tall. It is worth laying out in one place, because the shape of it is the point. The bottom rung is parallax, pure geometry, no assumptions, and it reaches the nearest few thousand light years. That rung has been rebuilt in our own lifetime, and the scale of the rebuild deserves saying. Bessel spent years on one star. A European spacecraft called Gaia, launched in 2013, spent a decade doing the same measurement on well over 1 billion of them. It worked by spinning slowly in space, sweeping its 2 telescopes across the sky again and again, and recording the position of everything it passed. Each star was measured dozens of times over the mission. Above the atmosphere, there is no blurring, so the angles it could resolve were tiny beyond anything possible from the ground. It measured shifts equivalent to the width of a human hair seen from 1,000 kilometers away. The result is the thing the whole ladder now stands on. A catalog of well over 1 billion stellar distances, measured by pure geometry, with no assumptions about brightness anywhere in it. Bessel got one. We have 1 billion. But notice that it is still local. Even Gaia's reach is a fraction of our own galaxy, and our galaxy is one of hundreds of billions. The bottom rung has become extraordinarily strong, and it has not become any longer. The second rung is Cepheids, calibrated using parallax measurements of the nearest ones. Reaches out to about 100 million light years, as we have just seen, and no further. The third rung is Type 1, a supernovae, calibrated by finding them in galaxies close enough to also contain measurable Cepheids. Reaches billions. The fourth rung is redshift, calibrated against the supernovae, and it reaches as far as we can detect anything at all. Look at how that is built. Each rung is anchored to the rung below it. There is no independent check at any level. The whole structure stands on the bottom step, and the bottom step is a handful of geometric measurements on nearby stars. Which means an error anywhere near the base does not stay near the base. It propagates all the way to the top, multiplied at every stage. This is not a hypothetical worry. It has already happened once in this story, and you have been carrying the evidence since Hubble's plate. Hubble measured Andromeda at 900,000 light-years. The true figure is about 2.5 million. He was out by nearly a factor of 3, and the reason was not carelessness at the eyepiece. It was that nobody yet knew there are 2 different kinds of Cepheid, following 2 different brightness relations. He was reading his stars off the wrong scale. The error was in the calibration of the second rung. Everything he built on top of it inherited the mistake, and there was no way to see it from inside the measurement. Exactly Herschel in the fog, 1 century and 1 method later. Correcting it in the 1950s roughly doubled the size of the known universe overnight, without anyone taking a single new photograph of anything far away. The photographs were fine. The ruler was wrong. There is a lesson in that which is bigger than astronomy, and it is the reason we have stopped here. A measurement is never just an observation. It is an observation plus a chain of assumptions, and the chain is usually invisible to the person holding the instrument. The observation can be flawless, and the answer can still be badly wrong. Every rung of this ladder has been rebuilt at least once for exactly that reason. The parallax base was redone from space, because the atmosphere blurs the tiny angles involved beyond what any ground telescope can reliably split. The Cepheid rung was split in two once the different populations were understood. Then it was reworked again, once the dimming effect of dust had been properly accounted for. The supernova rung had to survive a discovery of its own. Type 1A explosions are not quite as identical as the neat physics suggests. They need a correction based on how quickly each one fades. None of that is a scandal. It is what the work looks like from the inside. But be suspicious of anyone quoting a cosmic distance without an error bar. And hold on to what the latter actually is. It is a chain of trust, not a single act of seeing. And there is one number right at the top where the chain is currently failing to agree with itself. The relation Hubble published in 1929 has a number in it. Speed divided by distance. It says how fast the universe is stretching, and because it does, it also says roughly how long the stretching has been going on. Run the expansion backwards at the observed rate, and you arrive at the moment when there was no space between anything. The size of the number tells you how far back that moment is. So the number is, in effect, the age of the universe, and it is possible to write it on one line. Hubble's value came out at about 500, in the units astronomers use for it. That figure implies an age of roughly 2 billion years, which was a serious problem because by the 1930s, the geologists had already dated rocks. Radioactive elements decay at rates that can be measured in a laboratory, and by counting what is decayed inside a mineral, you can say how long it has been sitting there. The oldest rocks then known were comfortably older than 2 billion years. So cosmology had produced a universe younger than the Earth inside it. This is worth pausing on because of how the argument was resolved. Nobody threw out the expansion. The evidence for it was too good. Nobody threw out radioactive dating either for the same reason. Two well-founded measurements disagreed, and the conclusion drawn was the right one, which is that something in the chain of assumptions behind one of them had to be wrong. It was the distance ladder, and specifically the Cepheid calibration we have just been through. Hubble's galaxies were much further away than he thought. Further galaxies at the same speeds mean slower stretching, which means an older universe. Every correction to the ladder pushed the number down and the age up. 500 became 250, then 100. Then the arguments got serious. By the 1970s, there were two camps, each led by a formidable observer, and they disagreed by a factor of 2. One group put the number near 100, the other put it near 50. That is not a rounding dispute. It is the difference between a universe of about 10 billion years and one of about 20. The argument ran for the better part of 40 years. Both sides were careful. Both sides were using real data. Neither could persuade the other because the disagreement did not live in the observations. It lived in the corrections applied to the observations. And there was no way to check the corrections without a better instrument. That is a large part of why the Hubble Space Telescope was built. Not the only reason, but a headline one. Get above the atmosphere, resolve Cepheids in far more distant galaxies, and settle the number. It worked. The Key project reported in 2001, and the answer came in at about 72, which is between the two camps and closer to the lower one. On that value, the age of the universe came out at around 13.5 billion years, comfortably older than any rock. The figure has been refined a little since, and we will come to where it sits now. But 40 years of argument closed. And then it opened again, from a direction nobody expected, and it is still open now. Here is the situation. There are two entirely separate ways to get the expansion rate, and they no longer agree. The first way is the latter, exactly as described. Parallax, then Cepheids, then supernovae, each calibrated on the one below, measured with the best telescopes available. That route gives a value of about 73. The second way does not use the latter at all. It uses the oldest light in the universe, which is where we are going next, and works out what the expansion rate must be to explain the pattern in it. That route gives about 67. 73 against 67. On its face, that looks like a small gap, and 30 years ago, it would have been a triumph of agreement. The problem is the error bars. Both methods have been refined until their uncertainties are down to a percent or two. And at that precision, the two answers do not overlap. They are not fuzzy versions of the same number. They are two different numbers, each measured to a confidence that ought to exclude the other. It has a name now: the Hubble tension. There are only three ways it can end, and they are worth laying out because they are quite different in what they would mean. The first is that there is an undiscovered systematic error in the latter, something in the Cepheid calibration, or the dust corrections, or the supernova standardization that is quietly skewing the result. This is the historically likely answer. It is what went wrong every previous time. But it has become harder to believe. The James Webb Space Telescope has gone back and measured again many of the same Cepheids at infrared wavelengths, where dust matters far less, specifically to test whether the latter is crooked. The Cepheids checked out. The latter held. The second possibility is a systematic error in the other method, in how the oldest light is interpreted. That interpretation depends on a model of what the universe contains, including the missing mass we have just been through, and something else we have not discussed yet. If the model is incomplete, the number it produces will be wrong in a way that no amount of care with a telescope would reveal. The third possibility is that both measurements are right and the physics is missing something. Some ingredient in the early universe that made it expand slightly differently than the standard model assumes. That would be the largest result in cosmology in decades, and it is the reason the tension is taken seriously rather than filed away. Nobody knows which. As of now, it is unresolved, and people who work on it professionally disagree about which way it will fall. Notice the shape of it, though, because we have been here before 3 times. Herschel's star counts were sound, and his answer was wrong, because an assumption about dust was buried inside the method and could not be seen from inside it. Shapley and Curtis both argued honestly and both got half of it wrong, for the same reason. Hubble's Andromeda distance was out by a factor of 3, because the ruler had 2 scales and nobody knew. Each time, the flaw was invisible from within the measurement, and each time it took a new and independent kind of observation to expose it. That is what the tension is now waiting for. Not a better argument, a different instrument. Which brings us to the other measurement, the one that does not use the latter at all. It arrived by accident in a field in New Jersey, and at first, everyone involved thought it was a fault in the equipment. In 1964, 2 radio astronomers at Bell Laboratories in New Jersey were trying to get rid of a noise. Arno Penzias and Robert Wilson had been given the use of a horn antenna at Holmdel. It was a large metal funnel, built originally to bounce signals off early communications satellites, and it was a beautifully quiet instrument for its time. They wanted to use it for radio astronomy, which meant they first had to account for every source of interference so that anything left over would be real. There was something left over, a faint, steady hiss, a bit under 3.5 degrees above absolute zero when converted into a temperature, and they could not make it go away. So they worked through the possibilities, and the list is a good demonstration of what careful means. They checked the antenna's own electronics. They checked for radar and radio stations. They pointed it at New York City to see whether the hiss went up, and it did not. They considered whether it might be coming from the atmosphere, but atmospheric noise changes as you tilt towards the horizon, and this did not. They wondered about leftover radiation from nuclear tests, and the timing did not fit. They also found a pair of pigeons nesting in the horn, evicted them, and cleaned out what Penzias later described in a paper as a white dielectric material. The pigeons came back. They were removed again by less gentle means. The hiss was unchanged. Whatever it was the same in every direction they pointed. It was the same by day and by night. It was the same in every season, which rules out anything connected to the Earth's position in its orbit. It was coming from everywhere at once, evenly, and it would not switch off. 30 miles away at Princeton, a group led by Robert Dick was building an instrument to look for exactly that. They had been working through the consequences of a hot early universe and had reached a firm prediction. If everything really was compressed and hot in the distant past, then that heat should still be around, diluted by all the expansion since, stretched to long wavelengths, and detectable as a faint uniform glow in every direction. They had worked out roughly what temperature to expect, and they were assembling a detector. A phone call connected the two groups. Penzias described the noise. Dicke put the receiver down, turned to his team, and told them they had been scooped. The two papers were published together in the same issue of the same journal. One reports a measurement of an unexplained excess. The other explains what the excess is. So what is it? Go back to the reversed film from earlier. Push the expansion far enough back and everything is compressed and extremely hot. Hot enough that atoms cannot hold together. Electrons are stripped away from nuclei and everything is a plasma of loose charged particles. A plasma like that is opaque, and the reason is specific. Light cannot travel in a straight line through it because free electrons scatter photons almost immediately. A photon goes a short distance, hits an electron, changes direction, hits another. It is not that the early universe was dark. It was blindingly bright and completely foggy in the way the inside of the sun is bright and foggy. No light could get anywhere. Then the expansion cooled it, and at about 380,000 years after the beginning, it dropped past a threshold. Nuclei captured electrons and held onto them. Neutral atoms formed, and a gas of neutral atoms is transparent. The fog cleared everywhere, at more or less the same time. At that instant, every photon that happened to be in flight suddenly had nothing to scatter off. It simply carried on traveling. And a very great many of them have been traveling ever since, without hitting anything for about 13.8 billion years. That is what the hiss is. It is the light released when the universe turned transparent, still arriving. It was not microwaves when it set out. It was something closer to a fierce, visible, and infrared glow, appropriate to a gas at a few thousand degrees. What happened to it on the journey is the expansion we have already met, applied to the light itself. Space stretched while the light crossed it, and the light stretched with it. The wavelengths were pulled out by a factor of over 1,000 from visible down into the microwave band. Which brings us to its temperature, and to a small correction. The figure Penzias and Wilson arrived at was rough, and they knew it because they were reading a faint signal on an instrument built for something else entirely. Measured properly, since the glow sits at 2.7 degrees above absolute zero. That is the number to keep. Which means the coldest thing anyone measures is also the oldest bright thing there is. Now the part that changes how you picture the sky. The glow does not come from a place. There is no object out there emitting it. It is coming from a time. Everywhere in the universe went transparent at once, so in whichever direction you look, you are looking back to the moment it happened, and you see it at the distance light has traveled since. It forms a complete shell around us, in every direction, at the same distance. Astronomers call it the surface of last scattering, which is precise and unlovely. It is the last place a photon bounced before it came to us, and it is a genuine wall. Not a wall you could reach or touch, and not the edge of anything. But you cannot see past it, and no improvement in telescopes will ever change that, because before that moment the universe was opaque. There is no light older than this light. The fog is behind it. There is one more thing in the signal, and it is the reason it has been measured over and over by satellites since. The glow is not perfectly smooth. There are variations in its temperature from patch to patch, and they are tiny. About 1 part in 100,000. Map them carefully and you get a modeled pattern across the whole sky. Finding them took 3 spacecraft and 30 years, and the sequence is a good illustration of how a measurement gets sharper. The first was launched in 1989. It confirmed that the glow has exactly the spectrum a hot object cooling should have, which was the strongest evidence yet that the hot early universe was real rather than a story. The match was so precise that when the result was shown at a conference, the room applauded. It also produced the first map of the variations, though at very coarse resolution, in patches several degrees across. The second, a decade later, sharpened the map by a large factor and pinned down the age of the universe to within a few percent for the first time. The third, launched in 2009, mapped the whole sky at higher resolution again, and its numbers are the ones still quoted. That is where the value of 67 comes from, the one that will not agree with the latter. Each mission measured the same ancient light. Each one simply resolved it more finely, and with every improvement, the variations stayed exactly where the previous mission had found them, which is the sort of agreement that makes people trust a result. Those patches are the density ripples of the early universe. Slightly denser regions were slightly hotter, and slightly denser regions are the ones where gravity had a head start, so they are the regions that went on to collapse into the first structures. Every galaxy in the deep field grew out of one of those patches. So did the Milky Way. So did the Sun, the Earth, the rocks the geologists dated, and everyone who has ever tried to measure any of it. That modeled map is a picture of the seeds, taken before any of them had grown, and it is the closest thing to a baby photograph the universe permits. The pattern also does something practical, and it is where that disagreement came from. The size of the patches depends on what the universe was made of and how fast it was expanding while the light was in flight. So you can read the expansion rate out of the map without touching a Cepheid or a supernova. That is the 67, standing against the latter's 73. And one last thing, which is worth going to sleep on. It is here. It has never stopped arriving. It is passing through the room, through the walls, through you, at a rate of enormous numbers of photons every second, and it has been doing so throughout your entire life. Before there were television aerials, a small measurable fraction of the static on an untuned analog set was this: the oldest light in the universe, arriving as a faint gray snow. You are inside the afterglow. Everyone always has been. There is a gap in the record, and it is enormous. and almost nobody mentions it. On one side of the gap is the oldest light, released when the fog cleared at 380,000 years. On the other side are the earliest galaxies, the faint red smudges in the deepest images, a few 100 million years in. Between those two, there is a stretch of time with nothing to see in it. Not because our instruments are too weak, because there was nothing emitting. Think about what the universe actually was at that point. The fog had cleared, so light could travel freely, but the light that had been released was already on its way, spreading out and cooling, and nothing new was being made. The matter was neutral hydrogen and helium, thin and cold and almost perfectly smooth, drifting apart. No stars. There had never been a star. Nothing anywhere in the universe was hot enough or dense enough to shine. The universe went dark. Genuinely, entirely dark, everywhere, for something like 100 to 200 million years. It is worth sitting with the scale of that. 100 million years is roughly the length of time between the first dinosaurs and now. For a period of that order, there was no light in the universe at all, beyond the fading afterglow. Nothing you could have seen by. Nothing that had a surface or a shape. Astronomers call it the Dark Ages, which for once is not an overstatement. What was happening was slow and invisible, and it was the most important thing that has ever happened. Remember the mottled pattern in the oldest light, the temperature variations of 1 part in 100,000. Those were regions where the matter was very slightly denser than average. Slightly denser means slightly stronger gravity. And gravity does not need any help. It only needs time. So through the whole of the dark period, those faint, denser regions were quietly pulling material in. Nothing dramatic. No event, just a very small imbalance compounding for 100 million years in the dark. The dark matter did most of the work, because there is 5 times more of it, and it does not push back against itself the way gas does. It collapsed first into a vast web of filaments and knots. Then the hydrogen fell into the wells the dark matter had already made. Eventually, somewhere, a knot of gas got dense enough and hot enough in the middle that hydrogen began to fuse. The first star. Nobody has seen one, and it is not clear that anyone ever will. But we can say what they must have been like, and they were not like anything now. Every star that forms today forms out of gas that has already been through other stars, so it contains carbon and oxygen and iron. Those elements matter enormously to how a star forms, because they radiate heat away efficiently, which lets a collapsing cloud cool and fragment into many small stars. The first clouds had none of that. Pure hydrogen and helium, nothing else, and a very poor ability to shed heat. So they did not fragment. They collapsed as holes. Which means the first stars were monsters. Hundreds of times the mass of the sun, blazing at temperatures nothing matches today, and correspondingly short-lived. A star like that does not last billions of years. It lasts a couple of million, and then it detonates. That detonation is the moment the universe started making everything else. Those first detonations forged the first heavy elements and scattered them into the surrounding gas. The next generation of stars formed out of slightly enriched material. The generation after that, more so. Every cycle added to the stock. The iron in your blood is at the end of that chain. So is the calcium in your teeth and the oxygen in the air in the room. It was all assembled inside stars over billions of years and passed down. The first link in the chain was forged in the dark by objects that no longer exist and were never observed. The light from those first stars did one more thing. It was fierce ultraviolet, and it began stripping electrons back off the neutral hydrogen that filled everything. Bubbles of ionized gas grew around the first sources, then merged until the whole universe had been turned back into plasma. That is called reionization, and it is the end of the Dark Ages. It took several 100 million years, and it is the last great change of state the universe has been through. Here is what is unsatisfying about all of it, and it is worth being honest rather than tidy. Almost none of that has been observed. The Dark Ages are, by definition, unobservable in visible light, because nothing was emitting. The first stars are gone. The reionization era sits right at the limit of what the best telescope can reach. That is exactly why Webb was built to look in the infrared. It is also why the galaxies it is finding at the very edge are being argued about rather than celebrated. So the story of the Dark Ages is largely inference. Good inference from the modeled map on one side and the earliest galaxies on the other, constrained at both ends and consistent with the physics in between. But it is the one chapter of this whole night that is reasoned rather than seen, and it is fair to hold it a little more loosely than the rest. That is a good position to be in before the last of it. What comes next is the inventory of what the universe is actually made of. Most of it turns out to be things nobody can identify at all. By the middle of the 1990s, the measuring had become good enough to ask a question that would have been meaningless a century earlier. Not how big is the universe, and not how old. What is it made of, and in what proportions? Two teams set out to answer part of that, and both of them expected the same result, and both of them were wrong. The question they were chasing was how quickly the expansion is slowing down. That it must be slowing seemed beyond argument. Everything in the universe pulls on everything else. Gravity is always attractive. It never pushes, and there is a great deal of matter. So the stretching that started at the beginning ought to be losing pace, in the way a thrown ball loses pace on the way up. The only real question was whether it would eventually stop and reverse, or coast outward forever. And the answer to that depends on how much matter there is. Measuring the deceleration needs the exploding stars from earlier. Find Type 1 a supernovae very far away, which means long ago, and see how fast the universe was expanding then. Compare that with how fast it is expanding nearby, which means now. The difference gives you the change in rate. Both teams found the same thing. Checked it, disbelieved it, and checked it again. The distant supernovae were fainter than they should have been. Fainter means further away than expected, which means that in the time since they exploded, the universe had stretched more than a decelerating universe could manage. The expansion is not slowing down. It has been speeding up for the last several billion years. Something is pushing space apart, and whatever it is currently winning against the combined gravity of everything that exists. It is called dark energy. The name is a placeholder, exactly as dark matter is a placeholder, and it is worth being clear about what is and is not known. That the acceleration is happening is measured from several independent directions, and 3 of the people who did it shared a Nobel Prize. What is doing it is not known at all. There is no accepted explanation. There is a number that fits, and no account of where the number comes from. The best guess is that empty space itself carries a small amount of energy. Not the objects in it, the vacuum, and a vacuum with energy in it behaves in the equations as a pressure that pushes outward. It is a very old idea. Einstein had put a term of exactly that form into his equations in 1917 to hold the universe still, and had removed it in embarrassment once expansion was measured. The term came back with the opposite sign and a different job. The trouble with that explanation is arithmetic. When physicists try to calculate how much energy empty space ought to contain, using the theory that governs the very small, the answer they get is larger than the measured value by some 120 orders of magnitude. That is not a discrepancy. It is the worst prediction in the history of physics, and nobody has resolved it. So the honest position on the largest component of the universe is that we can measure it accurately and cannot explain it at all. Now put the whole inventory together, because this is the part of the story that would have astonished everyone in it. Ordinary matter, the kind that atoms are made of, accounts for about 5% of the energy content of the universe. That is everything. Every star, every planet, every galaxy in the deep field, every rock the geologists dated, every person who has ever looked up. Dark matter, the mass that is not there, is about 27%, 5 times as much as the visible kind, holding the galaxies together, undetected in any laboratory. Dark energy is the remaining 68% or so, pushing everything apart and unexplained. Which means that the entire history of astronomy, from the first person who noticed the stars move to the deepest image ever taken, has been the study of 5% of what there is. And it is worse than that, in a way that is quite funny if you look at it from the right angle. Of that 5%, most is thin hydrogen and helium spread through intergalactic space, too diffuse and too cool to shine. The part that actually glows, the part visible in every photograph in this story, is a fraction of a fraction. Go back to Herschel at the start of the night, working through his gauges. We already know he had the size badly wrong. What is stranger is that he was also, with no possible way of knowing it, counting the wrong thing entirely. Stars are not what the universe is mostly made of. They are the sparks on top of it. There is one more thing the inventory does, and it is the reason it matters for what comes last, rather than being a footnote. The proportions are not fixed. They change as the universe expands, and they change at different rates. Matter thins out as space grows. Spread the same amount of matter through a larger volume and its density falls. But if dark energy is a property of space itself, then more space simply means more of it. Its density stays the same while everything else dilutes, so the balance shifts permanently and in one direction. Early on, matter dominated, gravity had the upper hand, and the expansion was indeed slowing. As space grew, matter thinned, dark energy did not, and at some point, a few billion years ago, the two crossed over. We live after the crossover, which means the acceleration is not a phase. On current understanding, it does not end. It gets stronger relative to everything else, forever. And that has a consequence for what can be measured, and by whom, and for how long. It is the last thing in this story, and it is the reason the story has a deadline. So here is the number, after 200 years of people counting things. The universe is about 13.8 billion years old, and the part of it we can see is about 93 billion light years across. Those two figures look as though one of them must be wrong. Light has only had 13.8 billion years to travel. So surely nothing can be further away than 13.8 billion light years, The whole thing should be about 27 billion light years wide. It is not, and the reason is the stretching. The light that is arriving now from the most distant galaxies set out a very long time ago when everything was much closer together. It has been traveling ever since. But while it traveled, the space it had already crossed kept expanding behind it, and the galaxy it came from kept being carried further away. So the light took 13 billion years to arrive, and the object that sent it is now around 46 billion light years off. The distance the light covered and the distance to the source are two different numbers. That is not a paradox. It is what happens when the road grows while you are walking it, which gives us an edge. And the edge is not the sort of thing people usually picture. It is not a wall in space. There is no boundary out there, no shell, nothing you could travel to and press your hand against. Suppose you could stand in the most distant galaxy we can see. You would find yourself in a perfectly ordinary place. There would be galaxies scattered around you in every direction, including a great many we cannot see from here. Your own observable universe would be a sphere of the same size, centered on you. Ours would be a sphere overlapping it. The edge is a limit in time, not in space. We can only see as far as light has had time to reach us. That is all it is. The horizon is a statement about how long the universe has existed, translated into a distance. What lies beyond it is, almost certainly, more of the same. Every large-scale measurement we can make says the universe is remarkably even. The same density of galaxies in every direction, the same faint glow from every part of the sky, the same physics wherever we look. There is no sign of an edge approaching, no thinning out, no evidence that our region is special in any way. So the honest expectation is that it carries on well past the horizon, and possibly without end. We cannot check. That is the first uncomfortable thing here. There is a permanent limit on the observable, and it is not a technological limit that a better telescope will push back. The second uncomfortable thing is worse, and it follows directly from what we have just counted. The expansion is accelerating, and the acceleration does not end. Here is what that does to the horizon. If the stretching is speeding up, then a galaxy far enough away is being carried from us faster than the light it emits can close the gap. Light that leaves it today will never arrive. Not late. Never. And the boundary at which that becomes true is moving inwards. More and more of what we can currently see is crossing over into the category of things we will never hear from again. Galaxies are not vanishing from the sky because the old light is still in transit. But the last light any given galaxy will ever send us has a date, and for a great many of them, that date has already passed. The observable universe is not filling up. It is emptying. Follow that forward far enough, and the sky becomes unrecognizable. In something like 100 billion years, every galaxy outside our own small gravitationally bound group will have receded beyond reach. The Milky Way and Andromeda will have merged long before, so there will be one galaxy, alone, with nothing visible outside it. Now think about what an astronomer would be able to work out at that point. No other galaxies, so no spiral smudges to argue about, no Cepheid in Andromeda, no redshift to plot against distance. The oldest light will have stretched so far that it is effectively undetectable. Nothing in the sky would suggest that the universe is expanding. Nothing would suggest it had a beginning. Nothing would suggest that anything at all exists beyond the one island of stars overhead. They would look out, measure carefully, and conclude that their galaxy is the universe. they would be as wrong as Shapley was. And unlike Shapley, they would have no way to find out, because the evidence would be gone rather than merely hidden. Which means the period in which this is discoverable is temporary. It is open now. It was not open in the deep past, when there were no stable atoms and nobody to look. It will not be open in the deep future. And we happen to be inside the window, holding the instruments at the one stretch of cosmic history when the answer can still be read off the sky. That is either an enormous piece of luck or a fairly humbling coincidence, and it is worth lying in the dark thinking about. One last thing, and it takes us back to where the night started. Herschel counted stars carefully and drew the wrong conclusion because he was inside a fog that his own method could not detect. We have caught that error, and we have caught the same shape of error 3 more times since, and each time the fix arrived from an unexpected direction. There is no particular reason to believe we have caught the last of them. The tension in the expansion rate might be exactly that, sitting in plain view and refusing to resolve. The 2/3 of the energy content that has a name and no explanation might be another. Somebody later may look at our numbers the way we look at a grindstone 6,000 light years wide. That is not a reason to distrust any of it. Every number in tonight's story was won by someone measuring more carefully than the person before them, and each correction made the picture larger rather than smaller. It is only a reason to hold the current answer the way the good ones held theirs, which is firmly and loosely. The measuring stops at 93 billion light years, not because anything is there, but because that is as far as the light has come. A wall we can never see past. It has been in front of us the whole time. That is where we will leave it. There is nothing else to do now, and nothing to remember. If you drifted off somewhere among the Cepheids and surfaced again just now, you did not miss a step. That was always the idea. If this helped you sleep, a like or a subscribe means the next one finds you on its own. Good night.